Okay, so someone asked me to go over the question 4 from the assignment. So that's this situation here. We got this beam. We've got a reaction supporting it. It's fixed at B here. And we've got this load here that's varying uniformly from a positive 900 newtons per meter. And again, I'd like to emphasize here, this is positive because these are pushing upwards on the beam. This is a negative because these are pushing downwards on the beam. So from a positive 900 newtons per meter on the one end of the beam to 1500 newtons per meter at the close end of the beam. So first off, I'd like to break this up into two triangles, because triangles I can work with, some sort of weird shape that goes positive and negative in certain portions. That I can't. So I just redrew this, exaggerating the scale a little bit. So what I need to do is I need to find out where that intercept is, and so I can get the areas, and so I can get where these things act. So basically what we have here is we've got a function. The function, the weighting function, has a certain slope. So if this is a 900 Newton per meter, and this is a negative 1500 newtons per meter distribution, and it varies over this 4 meters, that means we've got a slope, right? We got a slope of its magnitude is 600 newtons per meter per meter, newtons per meter squared. So so anyways, so I got this. We've got a function here. We can solve for where the intercept is relatively simply. So that'll just be at x is equal to 900 divided by 600, so 1.4 meters. So this is 1.4 meters. Sorry, 1.5 meters. 1.5 meters, and this is 2.5 meters here, which looks about right to me, right? So I'll just redraw that here. Drawing our free body diagram, we've got this distribution here, we've got this distribution here, we've got our reactions. We want to replace those distributions with their equivalent local point loads. So going ahead and doing that, we need the magnitude and we need the location. So this one here has a magnitude of 900 times the 1.5 meters, 900 newtons per meter times 1.5 meters divided by 2 because it's a triangle and not a box. So base times height over 2. So that'll be 675 newtons for this for the positive forces acting upwards, and then for the triangle with the negative forces, got the 1500 newtons per meter times 2.5 meters, and again divided by 2. So that gives us 1875. 1875, 675. So where are those located? Well, okay, so we know that the equivalent, we know that the centroid of a triangle is located, it's 1/3 of the way from it's 1/3 of the way from the 1/3 of the way from the fat end, 2/3 of the way from the tip. So this one here, that'll be located 0.833 meters from B, which is just 2.5 meters divided by 3. So that's 1/3 of the way from here to here. sorry, one third of the way from here to here. Same deal on this other end. So this thing is 1.5 meters. So we're measuring from this end. It's half a meter here. So this will be 1/2 a meter from the far end, or of course measured from B, 4 meters minus half a meter. That's 3.5 meters. So that's where those are located. So we got our free body diagram. We've got 3 unknowns, and we can solve for those. So the force in the y direction is equal to 0. The sum of the forces in the y direction is equal to 0. Let's just add those up. We got By. We got the minus 1875, and we got the positive 675. That's equal to 0. 875 minus 675 is equal to By, gives us 1200 newtons. Fx is equal to 0. Well, the only one that's acting in the next direction is B, so it is Bx, so Bx is 0. Not that shocking. We see that fairly often here, don't we? And then we got our moment about B. Let's take the moment about B. So taking that, we will have, I'm just going to quick sketch here. So we got the reaction moment. We have the 1875 newtons times the 0.833 meters. That's going to be a positive because, again, taken about this point, that's causing counterclockwise rotation. And then we got the 675 Newton force times its 3.5 meters. Oh, I realized I had times 3.53 meters. Gone a bit off the page there for you guys. Here, let's. There we go. Okay, 675 times 3.5, and again that'll be a negative moment because we are going clockwise with that thing. So this times that, move it over to the other side, subtract this. That gives us 800 Newton meters once we do the math for our reaction. So there's the last of our reactions. So our actual reaction, and when we got this distributed load. It's going to cause a reaction like this. 1200 newtons. I know it looks more like a 3, but oh well. And it's going to cause a reaction of 800 Newton meters.